Thanks. So it's a pleasure to speak here at my very first MOND conference. So far I've always been interested in MOND, but I started working on it relatively recently, about a year ago. Okay, so in my talk, I'm going to be discussing from the point of view of MOND and Newtonian N the origin of the dark halo or total galaxy mass ratio versus ellipticity in elliptical galaxies. Okay, so recently there has been a few papers came out, an observational paper came out on this relation between the mass-to-light ratio of elliptical galaxies and their ellipticity measured as a function of the apparent ellipticity in the assumption of lateness of elliptical galaxies. And this relation can be translated from mass-to-light ratio in terms of total mass, if one believes in the presence of dark matter, over baryonic mass versus intrinsic ellipticity. And interestingly enough, actually strikingly, it's a linear relation. So in order to obtain these empirical relation, a large sample of 237 elliptical galaxies has been taken from different surveys and with rather strict criteria outside. So only medium-sized galaxies within a mass range of 10 to the 10 up to 10 to 11 solar masses, undisturbed, so not in direct interaction with neighboring galaxies. And therefore there has been a lot of rejections like compact ellipticals, all the active galaxies, everything that could be, let's say, called peculiar, and also high sigma galaxies at large redshift in order to exclude the S0 from the sample. If you go to higher redshift, however, all these top criteria here have been relaxed. Okay. And again, a lot of different and independent methods to estimate the mass-to-light ratio have been used. The usual Deur theorem, stellar dynamical models, X-ray, and also dynamics of satellites or planetary nebula, gas disk dynamic, and finally lensing. So these are some 4 plots taken from the original paper by Deur in 2014 showing the linear relation between the mass-to-light ratio versus the apparent or the intrinsic ellipticity in the case of the oldest sample here. And this is a rather good scatter. And these are more recent data from reprocessed by the same group for newer and much better observational data. And still, this fairly linear relation seems to hold. Of course, this has, if true, it is something serendipitous that has no real basis. It's true, this has quite a few implications, astrophysical implications, both in the dark matter scenario and in the MOND scenario that we're interested in. First of all, in the case of dark matter, so this means that the more dark matter you have, so the larger is the halo with respect to the baryonic component, and the larger the departure from the spherical symmetry one would be observed. Then this appears to be in apparent contradiction with the standard galaxy formation scenarios. And therefore, this implies that more massive halos, if there is dark matter, should be less spherical. Well, in MOND, larger spheroids should depart more from spherical symmetry if the only contributor to the mass-to-light ratio is the baryonic mass. So far, no evidence of relations between mass-to-light ratio or total mass versus baryonic mass has been observed in N-body simulations of galaxy formation. Well, in reality, this has never been looked in detail. And what I'm doing here in in this work, which is actually at a very embryonic state, it's not published, is to perform a large set of N-body simulation of galaxy formation in both Lambda-CDM scenario and MOND, using a broad set of initial conditions. For example, for the dark matter simulations, there are we played with isolated cold collapses within a spherical frozen halo or a light halo whose mass could be changed in different experiments, or clumpy collapses where virialized clumps merge together, or non-virialized clumps merge together in cold fixed halos, or light halos that are also allowed to evolve. While in MOND, they performed spherical monadistical cold collapses, or merging of already virialized or non-virialized substructure. And last but not least, we also performed simulations of spherical Ozipkov-Merritt's unstable radial anisotropy model in both MOND and dark matter. So first of all, let's have a look at the setup where the thing doesn't work. So here I showed the final total mass versus total mass in units of the baryonic mass versus the intrinsic or the projected ellipticity for some collapses, monolithic collapses in the dark matter scenario for a broad range of halo to total mass, halo to baryonic mass separations. Here in purple, there's the Deur 2014 linear relation, and the blue shaded area is just the scatter, the original scatter derived from the observational studies. And then we see that the simulated Newtonian models do not match in any case the empirical observational relation. Well, different symbol refer to different type of initial conditions. Just that you know, the squares are a gamma model with gamma equal 1 collapsed into also in gamma equal 1 gamma model halo with the same initial radius, while the gray circles are gamma models collapsing into larger halos with the same radius 10 times the initial rates of the whole dark matter. And in no case this seems to reproduce the linear observation linear relation. Again, these are other numerical experiments with frozen and live halos with a broader range of in total mass to baryonic mass ratio for spherical initial condition and clumpier simulation. So in a way, there is some trend that indicates that more massive halo or larger halo contribution results in a more flattened end state. If the halo is not allowed to evolve, so it stays spherical and just provides a background potential for the variance. When the thing becomes a little bit trickier with, this at least as I said for frozen halo. When you have live halos, so you're allowed to have the feedback of variance onto the dark matter, the situation becomes completely opposite. So one finds what one would expect at large mass to total mass to baryon mass ratio. The system is less flat. If one goes to initial condition with a clumpier, if you go to clumpier initial conditions, so where you merge a smaller substructure within a broader collapsing structure, then for clumpy initial conditions with light halo, there's pretty much no difference in the final ellipticity, as no matter what is your assumed or total mass to periodic mass. Halo, while again, if you freeze the halo, some sort of trend that's larger, more massive object have a higher ellipticity appears. So this so far was for the ellipticity. Here I'm just plotting for all these sets of simulation the relationship between the period velocity dispersion within the Lagrangian radius containing the 50% of mass and the total mass to periodic mass ratio. So let us go to MOND simulations. So here I'm plotting again the central period velocity dispersion versus the final ellipticity of the baryonic component. Here we have only variance for a broad range of simulations in MOND, MOND parallel, which are the black squares, while the red triangles are all the other runs, the end products of the other runs in the Newtonian graphs. You can see that there is some trend that system with a larger central velocity dispersion or variable velocity dispersion are associated with larger ellipticity. This is intrinsic ellipticity, not the projected ellipticity. Okay, so in order to compare what happens in the two paradigms, one has to find a proxy of what would be the dark matter in a MOND simulations. So we computed the density distribution of the equivalent Newtonian system for all our MOND simulations, where the equivalent Newtonian system is simply the system with dark matter whose baryon distribution is the same of that of the final state of the MOND simulation, and the force field and potential is such that one requires an extra density distribution which constitutes the dark matter. So within this, for reasons of simplicity, in a, so to say, spherical approximation, so the final state of the MOND simulations is always an ellipsoid, either prolate or plate, but we assume that the spherical the dark matter halo to be spherical. So basically, we neglect the solenoidal term, and would come out when one would eliminate the density between the nonlinear Poisson equation or MOND field equation and the standard Poisson equation of Newtonian gravity. So more on this will be detailed in Federico Re's poster session, if you're interested. Okay, and so what happens? So if we plot what would be the total mass to baryonic mass versus ellipticity in MOND systems, surprisingly, or maybe not surprisingly, the trend is pretty much the same as what we observed for some of the Newtonian simulations. So that more flattened objects, so end states that depart more from the spherical symmetry are characterized by a larger total mass to baryonic mass in terms of, of course, of the mass of the equivalent Newtonian system. And interestingly enough, in the MOND simulation, we never have, or at least in this case, we never have systems that are more flattened than an E7 at variance with what happens in Newtonian gravity with frozen halos, where we can obtain very high ellipticities that are observed in elliptical galaxies. So another thing that's been looked at is the relationship between in all these, both MOND and Newtonian simulations. We've been looking at the relation between the anisotropy parameter the end states versus the ellipticity. And it seems that there's a sort of correlation in both, so these are mixed, both Newtonian and MOND simulation. There seems to be some relation between the ellipticity and the anisotropy parameter, with less spherical system associated with a larger degree of radial anisotropy quantified here by the relation between the kinetic energy stored in radial orbits versus tangential orbits. And so this is the evolution of, say, quantity in MOND and Newton simulation, and also up here the evolution of not the ellipticity, but minimum to maximum axis ratio and intermediate to maximum axis ratios. So whenever we speak of anisotropy, radial anisotropy related thing, it smells like radial orbit instability. I mean, in both MOND and DM simulation. So for those that don't know the few words, the radial orbit instability is a quite pretty dynamical mechanism that even if you start from perfectly spherical initial condition where a lot of energy is stored in high angular momentum orbits, you end up by a this instability in triaxial or flattened end states. And it should be related on an accumulation mechanism of orbits with frequencies close to the precession orbits to a substructure that then amplifies itself more and more and then turns something that was spherical into a flattened or non-spherical system. So, I mean, there have been, to conclude, and I'm close to conclusions. This seems to be the radial orbit instability seems to be the driving phenomena in both paradigm to obtain spherical system. And so far, the radial orbit instability has been studied also in MOND. And the conclusion of this, very certainly that MOND systems are more stable than single component Newtonian system without dark matter with the same density profile and also the same amount of anisotropy. But MOND systems are less stable than equivalent Newtonian counterparts, so where the initial potential of baryons plus dark matter is the same as in the MOND model. So this might be the explanation why in MOND we see even more elliptical systems at fixed mass, total mass to baryonic mass. Okay, so this is the same point as before, but for the ellipticity and not for the accelerations. And with that, I will go directly to my conclusions, since this was a very preliminary work. So even in MOND, so in both MOND and Newton simulation, there appear to be relation between the ellipticity and mass ratio relation, but somehow it's far from being the linear relationship observed in observational studies. So there's no way to reproduce the linear trend, at least for the set of simulations presented in the study. And it seems that the initial amount of radial anisotropy is the driving mechanism in both scenarios. This would therefore, in the absence of dark matter, maybe imply in the context of MOND a relationship between mass and anisotropy and final flattening in a galaxy formation scenario. So I am practically done. That was pretty much everything I wanted to say. So thank you for the attention and questions. So the total mass in the equivalent Newtonian system. So it's yeah, it's defined into the largest radius attained by the particle simulating the barrier components. I forgot to say that. So the total mass, I derived the density profile for the equivalent Newtonian system and integrate it up to the radius where baryonic mass ends, and then take the mass that I find inside that sphere as the mass of the observation. I mean, observationally is always in the observational skies. So as far as what I have understood from the observational papers, it's always the mass within the radius. It's the inferred mass, either measured with virial theorem or gravitational dancing, within the radius on which the ellipticity has been measured. Sorry?
Shouldn't have any particular physical meaning why you choose this area.
I agree. So the criterion used to analyze the numerical simulation is exactly the same arbitrary criterion of the observational studies. Unfortunately, that doesn't reproduce the same linear relation. Maybe that's the reason why.
I'll take a moment to ask a question myself, because what you say about the simulations, both Newtonian and MOND, sort of comport with my intuition for what ought to be going on there. But I really don't understand the observation lie, and you sort of said, well, it looks like this linear relation with the ellipticity, but you have any feel for how much would you believe that?
Oh, well, if you want the answer, I don't. So that's that's the reason behind, that's just the reason behind this story here. I don't buy it. I mean, I just try to see what happens in a simulations box. Perhaps now I believe even less.
So, since this relation between mass discrepancy and degree of flatness can be explained also in MOND, this might also explain the fact why globular clusters, which are quite roundish objects, have a Newtonian behavior, not a Mondian one. So this can, in principle, solve this issue observed that was attributed to MOND in the description of globular clusters.
Well, it's a rather bold statement. I would have excluded it, but I would say that globular clusters are that spherical because they are conditional systems. So the original processes sort of disrupt everything conditionless that would lead to non-spherical density profile. But yeah, could be. But then on the other hand, you also have the dwarf galaxies that are entirely massive dominated, but look rather spherical. And they pretty much have the same amount of stars.
Generally, they are flatter than globular clusters.
Sorry? Yeah, slightly flatter than globular clusters. Yes, I agree. So perhaps if there is such a relation, it's more monotonic. So it's there's an intermediate region where you have the maximum of the loss ratio versus the maximum relation.
Okay, so my intuition is there's no any physical reason behind this. I guess the real reason why you see such a correlation is due to your method, because you calculate the total mass from the loss dispersion, right? In the spherical symmetrical stuff distributions, you pick all those galaxies to calculate the total mass based on a spherical distribution. You have like some more concentrated in a relatively thin band, so you probably get a high total mass. That's probably due to your approach, not true physical reason. You maybe try to check that by reject some samples. So you say if you have a spherical systems and you reject some of the samples, make it wrong.
Yeah, I've assumed the spherical symmetry for the A, and then integrated the density profile that I would get, subtracted
Yeah.
and then also from the velocity dispersion. I get rather low, but of course the spherical representation is higher, but not dramatically higher.
Your correlation is not very strong, right? Slightly.
So I will pass on the fact that globular clusters are spherical.
Sorry?
No, I will pass on the fact that globular clusters are not necessarily spherical. I would like to know how you did your initial condition for the simulations to get self-consistent galaxies in MOND. Can you explain how you have been doing so?
I'm sorry?
Have you done your initial condition in MOND to be self-consistent?
The initial condition and the MOND initial condition, I mean, is always either cold, so it's everything with zero initial period ratio, or with spherical distribution, and then local Maxwellian approximation and renormalizing the velocities in order to get the wanted value of period ratio.
So it wasn't really variable at the beginning, right? It wasn't a self-consistent model.
Sorry?
It wasn't a self-consistent model initially.
The self-consistent model is just a few, and then I mean solving the Edgenton relation for computing the phase-space distribution function for the MOND system with the MOND potential, and then
I think it's
assigning
talking about structure formation, astrological structure formation, right?
But these versions have been. So you mean the simulation with radial orbital instability?
Yes.
Yeah. So this is just sampling. There's a few of them, and then sampling the phase-space distribution that you would get integrating numerically the Edgenton inversion formula using the MOND potential for a given density. And then for the others, it's just a distribution of a Poissonian distribution of clumps within a broader spherical structure. And again, local Maxwellian approximation for the velocities, not choosing any particular bias in the direction, and then renormalizing everything to the wanted value of the ratio. Yeah, that's pretty.
Federico Lelli, Arcetro Observatory. So you have a question about the radial orbit instability. So an important observational result from the integral field spectroscopic surveys is that essentially the vast majority of ellipticals are rotating, and large fraction of the flattening is driven by the rotational support, and the truly pressure supported ellipticals are more complex structural systems, but they are a minority of the population. So I was wondering whether if one starts from more realistic initial conditions in which you actually have a net rotation in the system, the radial orbit instability is gonna be reduced or not a problem
Whether
at
it's
all.
reduced or enhanced.
Well, it should be reduced, I guess. So, I mean, yeah. I mean, I wonder whether,
Well, it depends. I mean,
Whether
it
it's a
depends on
problem
the
or
formula
not
of the
in the
velocity
real
distribution
situation.
in the co-rotating frame at a given radius. I guess it depends on that. It's not, I wouldn't say that it's suppressed by rotation, but this would be the next step. So I haven't done anything.
My guess is that it's suppressed, but yeah. You can check it out.
But the other way around too, what's actually in that data sample? I mean, you said how it was cleanly expressed, but if there's some rotating thing.
Yeah, I mean, I was just thinking from the theoretical perspective because, the radial orbit instability has been posed as a potential problem for MOND because, an elliptical galaxy would be unstable. But if the elliptical galaxy is partially supported by rotation, as we observe, then that's not a problem anymore, I suppose. But it will reduce. Right.
Other questions for this speaker? Okay.
Sorry if I missed the initial part of your talk, but so for the MOND case, you set up the galaxies, since it's an N-body simulation, you set up the galaxies in spherical symmetry. How do you set up the galaxies?
No, not always. I mean, some of them are set up in spherical symmetry. Some other have clumpy initial conditions. So you have a spherical structure and then sub-clumps with.
So you mean like you set up a galaxy based on observations, and then you see the change of eccentricity. Is that what you're? Ellipticity. Sorry, ellipticity. That's what you do.
That's right.
Will you be doing hydrodynamical simulations of this?
Well,
Because I mean the reason I ask is because in MOND simulations a cloud of gas is shown to fragment, and these fragments fall into the main clump, which affects the ellipticity quite a bit if you catch it at the right time. With just the N-body, I'm not sure if you can grasp the entire picture, because I don't know if you have any fragmentation or something. I don't think so.
no, but this is really something extremely preliminary.
Okay.
So it's really
Okay.
stage 0, as we're saying. Perhaps in the future.
Okay.
Hi, Tarek, University of Oxford. Just a quick note, the process of the baryon schooling to the centre of the halo, I think, is meant to make the halo more spherical. And people have done comparisons between Hydra and N-body simulations. I'm not sure how big the effect is, but worth checking out.
All right, so I think we should transition towards discussion. Thank you, speakers.